Hello! Are you still awake? Still not sleeping? Woo! Yeah! Great. So, we have one last speaker today on our stage, and he is a mathematician. He almost got his PhD. I think he's almost got it. Or you got it already? No, he almost got it. Okay. He's from Web3 Foundation. And he's going to talk about interesting things about cryptography. So let's welcome on our stage Syed. Syed, right?
Yeah, Syed, yeah, thank you very much. Cool. Thank you for intro. Okay, so that is, thank you for coming. So this is the talk we are going through today. So I'm just going over what I'm going to talk about, if it works, which it doesn't. Oh, sorry. Okay. So I give a quick introduction at what I do in my life, and then give you some motivation, some situations that this big brother, this single point of failures, fails people and fails us, and why. So motivate you why we need to replace them, and then I talk about the cryptographic primitives that we can put and take these big brothers out and put this instead, so we get a better resilience system. Just a quick introduction to what we do at Web3 Foundations. I'm a researcher there. We invent, implement new cryptographic algorithm. The goal of Web3 Foundation is to support decentralized software, and the product mostly we work on is Polkadot, is a multi-chain network, and its goal is make decentralized systems much cheaper, much faster, much more efficient, in a way that we can compete with the centralized world. Moving on, I'm talking about the big brothers that we have in this world, and how they can make problem for our applications. So talking about Apple, WhatsApp and Signal, Google, Windows, just for some example that how they become dangerous or in the way. But there's many of them, you know. Anytime you use something centralized, you know, you're opening yourself to the possible failure. So this one is very recent. So there was this application called ICE block. So ICE stands for Immigration and Custom Enforcement for US. And basically what was it? People were reporting agent that they see. So basically there's a central database. You have the app on your phone. You see an agent in your neighborhood. You click. You say, I'm near an agent. And then it would go upload in iCloud, which is handled by Apple. And then, so that's you report. And then what will happen is that the Apple system, basically you can ask Apple, say, I want for this location, anybody near 5 miles of this and has my app, send them a push notification. And so that was the system, how it worked, and they had lots of users, I would assume in millions. And basically it was helping people just to hide when they see a ICE agent nearby. Now, the problem here is that Apple completely control everything here, right? So, and actually the developer, who for some reason didn't even open source the software, thought that's the feature. So they, in part, refused even to publish an Android version based on this reason, that they call it a privacy concern. So what is the point here is that on iOS, you could tell Apple, anybody near this location, send them a push notification. They would, the developer, the app does not get any data from people who get the push. While in Android would give you the identification, and then you send a push notification for them. And their idea was that if they get a warrant from the judge, then they have to give all the IDs in Android that send them, that they send a push notification to. And then, for example, then, ICE will get that IDs and then go and find them like where they are, in theory. The idea here is that, as the Graph and OS people were saying, is that this is not, the judge does not need to give the warrant to the app developer. They can just bring it to Apple. And even before here, Apple was giving information to law enforcement even without court warrant. So the opinion of the developer that why shouldn't we do it for Android was completely false. And so eventually what happened with the big brothers, this happened. So Apple, basically, the government of US contacted Apple and told Apple to remove it. And Apple removed it because they have other things to do in their life. They don't want to deal with the government. And the worst thing here is that on Android, you can install apps that are not in the app stores. But here in US, because the custom protection is less than Europe, in Europe you can also install apps that are not in the app store. But in US, you only can install apps that are in app store. So it's like a super big brother. Apple doesn't want to put your app there, and nobody else has any way to install it. They can decide not to send a notification. They can cut your access to the iCloud. The whole system falls apart. You have millions of users, and after that, nothing. You can do nothing with your. I mean, you had a mission, you had a goal, and everything fell apart. Next example is Signal and WhatsApp. So at least Signal is open source, and it supports end-to-end encryption. So what happened in the story is that UK passed this Online Safety Act, and all around the Western world there's defender for this act mainly because the intelligence agency don't like encryption. So this act basically says, if I go to the provider, they have to inspect the encrypted content, which already is a weird thing. If it's encrypted, if it's end-to-end encrypted, I don't have the key, right? I don't have the key to that content. How can I inspect? So basically, they want them to WhatsApp and Signal to scan end-to-end encryption messages if they ask for it. And obviously, the reply is that I cannot, is end-to-end encrypted. Then they came up with this solution. So they ask them to hash. They're very, very worried about the images for some reason, I don't know. But anyway, so they hash the image. You send the image to your friend. The message is end-to-end encrypted. So your image is encrypted. But they ask them to hash the image, hash the image, which is like scrambling this image all in one fingerprint, and send it to basically law enforcement. So anybody, or keep the hash, basically keep the hash on the Signal server. And then, when the law enforcement comes and says, send me the hash of those images. And the law enforcement also has all the hash of all the images that they are suspecting in their central database. And then they come to Signal and say, send me the hash, and then I'm going to compare the hash. And if they match, then I know this user was talking about like child porn content or terrorism or whatever they think. The problem is that, if there's a protest and the protesters sharing the hash, the government also can use it. So the hash is unencrypted, and they send it there. So they can compare the hash. Yeah. So the result was, OK, Signal said, and WhatsApp, both of them, they said, if UK government come to me and say do that, then I'm going to cease operation in UK. Because, that's the point of what they want. But that is not the point. Then, you are a single point of failure. You wanted to give end-to-end encryption to people, to provide it to that, and then, the government says you cannot do it, then Signal will go down, and then what do people do? They move from the end-to-end encrypted platform to those that are not end-to-end encrypted, and then they lose their protection. This is not, seems a working solution. Another example, Google. So I did this basically. I took my Android, I installed a free operating system on it. So I took off Android and installed Lineage OS. And then stuff stopped working. So Google Wallet stopped working immediately. It says, oh, you touched your bootloader. Basically, you unlocked it to install another OS that I didn't want, and so I'm not going to work with you. That is completely outreach. Like, you're providing with the credit card service, what is your business with my bootloader? But that's it. It's Big Brother. It controls everything. They can overnight say, OK, you cannot use your thing. Worse than that was my bank account. I tried to install my bank account. First of all, it gives me an OTP specifically from the bank. Like they send their password provider, and they say, you have to install this. And I say, OK, I'm installing this. And then what happened is that their OTP wanted to use some Google Play services completely. I don't know why. Is that OTP, the OTP, you are encrypting the time with your seed, and you get a number every 1 minute, basically. You really, I don't know what is the relation between Google Play service and this, but then basically they blocked my bank account because I used the free operating system. And this one, Richard Stallman, categorized Windows as a malware, and that is what he says. So he says it has a universal backdoor, basically. Microsoft can install anything on your Windows without even asking for your permission. So an example of this, which is a bit controversial, but I just wanted to talk about it, it was a botnet that was using Tor. So it's a malware that comes on your computer, install Tor, and start attacking other websites through Tor. So what happened, the Tor network traffic went very high. So Tor network, the Tor people, they were not very, very, very excited about it because, you know, it increased the consumption of the network. And then what happened is that one day Microsoft emailed Tor and said, what is the probability that a user put the Tor executable into a /Windows/System32? And Tor replied to them that, you know, it's not very probable. And then the day after, all the botnet disappeared. So what happened, Microsoft had pushed the update that went on the System32 and deleted that file, which you might think that is a good thing because it was a botnet and was harming people. But the idea is that Microsoft can come into your computer and delete anything they want at any time they want. You know, you have no control over it. That was an example of situation that happens when a player has so much power as a central service, be Microsoft or be Google or be Signal, even Signal. You know, all the messages go through Signal Saver, and then that point fails, and then you have no action, like it fails, and then you have no escape from it. So we want to design systems that, you know, they don't have this type of big point that control everything. To do that, we want to see first, why do we go to these big brothers, these big providers, and what do we want from it? So we go for various types of protection to these people. That is why we turn to these big services. So one of them is privacy, which we can eventually replace with encryption, you know. But we want our data to be private, and then we use this big provider, and just we trust them with the privacy. We go them for trust and integrity. We think that, you know, if my data is on iCloud, then nobody else will change it. I don't want to put it like open in the internet, or, you know, like the developer says, okay, I ask Apple to send a push notification. They are going to send it because I'm trusting them. Authentication, yeah. So you use them, you trust them because they will go out authenticate the users. Data and service availability, you always, your data, you leave it with them because with a high probability you think your data will be there next time you want it. Or you use Amazon AWS service, you know that, it's probably their service is up, so if your app is on that, and then it's probably working. And then identification. Identification is more complicated, but usually we go to government for identification of people, like If I want to ID somebody, either I ask for their passport or maybe phone number, but the phone number is because you thought that they use their passport to get their phone number, stuff like that. And the idea is that can we just replace either of this protection that we're asking from these big providers with something more using cryptography and using distributed service? Can we replace all this? And then as a result, we do not need to have a big brother in our system that can fail for various reasons. And then our system will become more resilient. So privacy with encryption. So part of the privacy that concern we have is encryption, right? So is basically you don't want your data to be revealed, and that can come with encryption, right? So that's an easy solution. And that is why end-to-end encryption should be by default set in every app you're using. Even if Apple is keeping your iCloud, they have nothing to do with to know what is inside that iCloud, for example. So what is encryption? Is to apply a mathematical function that's we don't know the inverse for it. We as a human being, we don't know how to find the inverse for it, and then it will change your data to the way that everybody else sees it, cannot inverse it. And so we have this from Snowden that this worked, right? So he was working for NSA, and then when he came out, he says basically a good encryption is one of the few things NSA hasn't figured out how to break. So basically, if you have a good encryption, then you can trust your privacy pretty well. You can put your data in open. You don't need to trust Apple to keep it secret for you. You can use encryption to keep it secret. And here, I want to branch to open source cryptography. So here, this is the basic principle of what cryptographer works on. It's called Kirchhoff's principle, and it basically says your encryption should stay encrypted no matter if everything about the system is known to anybody else. The only thing that shouldn't be known is the key. So when you design a crypto system, you cannot hide any part of it, any code, anything else. And basically that means if you have a good cryptographic system, it should be open source. If your system is not open source, you're violating this principle, and basically you cannot be trusted. An example of it is this company, Crypto AG, which was a Swiss company, and basically was selling ciphers to around the world. And eventually, it was closed source. At the time, I guess open source was not that big thing, and people actually thought, oh, it's an encryption system, so nobody should know about it. And basically, they secretly got bought by NSA and the German intelligence agency, and got money from NSA to basically break the crypto. Basically, they were designing broken crypto systems and sold it to Iran and Libya, and then West completely had access to their encrypted systems. So you cannot really trust closed source crypto. So let's decide from now if somebody is closed source, I don't know, the encryption of the NTFS system that comes with Microsoft, probably you cannot trust it at all. The interesting thing about Crypto AG was that they would sell product that they look completely the same, they have the same name, but when they sell it to Iran, they would bug it and they sell it to somebody else who was different. So, when you don't have open source, you don't have reliable compiling situation to see exactly, I built exactly the same thing that you built, so my product is the same as yours. The other example is actually the crypto was open, but the design was closed, and it resulted in this. It's called dual elliptic curve deterministic random bit generator, which is not random, it's deterministic, so it's a pseudo-random number generator, but they call it this way. So early 2000, NSA went to ANSI and said, can you make this a standard? This is a very good thing, and they gave the design, and they said, this is how people are going to generate random numbers. You give some seed to it, and then you generate random numbers, and using that random numbers, then you're going to generate your keys. 2004, RSA makes this a standard and publish it in their BSafe. So BSafe is a standard that US governments ask people, all companies that work with the federal government, they have to follow, they have to use tools that adhere to this standard BSafe. And they made this dual EC double random bit generator as a part of this. And basically, it was that if you want to do, in public key crypto, you want to use key, generate key, you have to use that. In 2007, so that Bruce Schneier, he published an article that says, did NSA actually put a backdoor there? And the idea was here. There was 2 prime number there, P and Q. And if this 2 prime number, they had a relationship that nobody else knows. Yes, so I'm going back, I'm getting back to this, but I love this crypto system works on the fact in a group that division is hard, right? So, so if you have these 2 points, and then one of them is multiplication of the other one, then the system is broken. But the only person who knows that this relationship exists is the person who generates this relationship. But this design comes from NSA and says use this. We have no way of proving that these 2 don't have this relationship. But if that relationship, so the article was saying, if that relationship exists, then the system is broken. And 2013, Snowden leaks the NSA document. 2013, basically Times says, publish an article that says actually NSA put a backdoor in exactly this because it was possible to do it. And actually, again, from the same leaked document, Reuters published that RSA got $10 million from NSA to actually put this in BSafe and implement it. So that is an example. The protocol could have been secure, but because they played with P and Q, the way that was it, the whole system broke, right? And that is the bad thing about the chain is like you generate the key can be predicted, and the whole thing after, even they are secure, because the key is not random, is broken. The lesson here was at least the process was public. And in public eyes, people looked at it and said, this might be broken, and they found out, and there was a loud warning and bell went off that, don't use it. Now, suppose it was a closed source crypto, you would know nothing about it, and they can do whatever they want. So that was about encryption. For authentication, we can use digital signatures, which again, you don't need any server or something to verify. You can, if you have the public key of the person, then they can use digital signature to authenticate that to you. I'm going a little bit the mathematics of this because I'm going to use it later, but that is most of the math that you will see in this talk, but I'm not going to more deep into that. But just going fast on the digital signature, just you hear this word secret key, public key, you will see how does it work. So you choose a secret key, which is suppose it's an integer, yes? You choose an integer as secret, you don't tell anybody about it. And then there is this mathematical structure that these are objects that you can multiply integer into them, and that is very easy. But if you want to divide them by that integer, it's very hard. So then basically what you do, you take one of these objects, you multiply, everybody knows that, the G, right? You multiply your key with this, which is basically you add this G S time together, and you get a new value, which is P. But the magic behind this is that I give you P, you do not, and you know G, and you know P, but you don't know how many times I added G to get P. Or you don't know basically what is the value that multiplied in G that you got P. And that is the base of this, the security of this crypto system is based on. So this is the most mathematical slide that you will see, and then after that, I just referred to it a few times. So I want to sign a message, right? So this is digital signature. This is my message. I want to prove that I give $1 million to somebody. I generate a random number K, okay, and I don't tell it to anybody. I multiply this k with the same g, that object that I could multiply with easily, but nobody knows what I multiply with. So if I reveal r, then nobody will know what was k, right? Because that's the property. Then I put this new r that I found, attach it to a message that I want to approve by signing, and I will hash it. So when I hash it, basically I scramble it, and I get some fingerprint from it. So this function just take these two together, scramble, and it's very hard for you to know what was the scramble that got that. And I get this e, which is the integer again. And then I write this relationship. So I get the key that I generated now. I multiply and I subtract e, the scramble value, times s, my secret key. And then whatever comes out of it, I send it to the port as my signature. So I give $1 million to XYZ, plus this is my signature, and everybody should be able to verify that. So how to verify it? You just need to note that k, the secret value that I have, is equal to this public value x. My signature has these two integers in it, plus e times s, which is my secret key. So if I have this, people cannot verify this, yes, because they don't have s. And they don't have s, they don't have k, they don't know. But if I multiply basically both sides by dg, this object that was easy to multiply but hard to divide, then I will get to this equation. And now, k times g was r, okay? X times g, I can do it because x was in the signature. I'm the person who is verifying the signature. I can multiply x by g. And I cannot multiply s by g, but I already know your public key. I know this public value from you, so I can just replace that with p. And e is public, so I can multiply it. As a result, I have the left of this, right? I can compute this. As a result, I can compute r. I know what you signed, give 1 million together. And I will put it in the scramble function, and I see if I exactly got the same e or not. So this is how digital signature work. But why did I bring it up? I wanted to talk about another concept. It's a zero-knowledge proof, which I come back to it when I want to replace some of this power that people have with something that doesn't rely on the big brother to do, and that's zero-knowledge proof. Here, this is an example of zero-knowledge proof. So in this process, I prove to you that I know S, right? I know S, the secret key, without revealing anything about S. So I'm telling you, I know a value that if I multiply with G, it gives me P, but I didn't tell you what it is. But at the end of the process, you are convinced that I knew S, otherwise I couldn't do this game. So this is an example of zero-knowledge proof. So I prove something to you without revealing any extra information. I didn't want you to know anything about my secret key, but I proved to you that I know the secret key. So this all brings me to OpenPGP and GPG. So OpenPGP is a standard of all this encryption algorithm and digital signature. And it's a pretty known standard, and GPG is an open source implementation of that. Is a GNU privacy guard and is heavily audited. That is very important in cryptography. You make a mistake, then your whole system will go down, or like NSA put something into it, and the whole system will go down. But this is heavily audited, so it's very good if you can use them in our projects, you know, and it's open source and free software, so it's there. And this will give us encryption and digital signature, which we can use for authentication and other stuff. The other missing piece that we don't have here is decentralization. So we got encryption, we got authentication, but we still don't have this, which is availability, you know. I have this server, and I go to Amazon AWS because most of the time, at least 99% of the time, is there, you know. As long as they're not pissed off at me and kick me out of their system, then I think it's always there, and then my customers won't be sad about it. While if I have a random server, then maybe it goes down, maybe my ISP doesn't work, maybe this and that. To mitigate that, you basically decentralize. You have many servers that are going to do that. These people here, I think, for example, you know, you copy your hard drive a few times, so if one of them fails, you can have more of it. More than that, decentralization will help you to put check and balance on the power, right? So this is how it works. You say, okay, don't trust one person, distribute the key between 4 people so they, at least 3 of them can get together and make a decision. So here, we are talking about free software and open source. FSF, the second high priority of FSF is decentralization. So what is concerning is that, we should be able to self-host, decentralize, and that's basically one of the critical part of having a free software, because at the moment you don't have this, you don't have a free service, Apple will close the iCloud, and you have nothing else to do. So I wanted to bring an example here that's called Delta Chat. You probably haven't heard of it, okay? And I want to compare it with Signal. So people in Delta Chat, they came and say, look, there's already a distributed resilient network. It's called email. While, a lot of people always use Gmail for their email, when they invented the internet, that was not how it was worked. They said every university have their own email server and this and that, and then these email servers should be able to talk to each other. So there are already a lot of email servers, and the network, or the email protocol is designed to have many, many email servers. So why not using that? And it's a messaging tool, they can talk to each other. So that's the thing. And then we have a reliable encryption and authentication protocols implemented in GPGs, which are already there. We can use it. And then they put this together, and then they made a messaging app that actually does not need a server, Like Signal, if UK government come to Delta Chat and say you have to do this, they don't exist, basically. There's just an app, which actually you can install on Android without the App Store. So if they come to App Store and say take it down, you can go and install from F-Droid and other market. So none of those stuff that Signal might fail in Delta Chat will fail. On the server side, you need to install email server, basically, which takes you maybe half an hour. All you need is to have a domain. You set up the domain, you say this is an email server, you put your credential in the DNS, and you run the script and you pull out a new server. So I did that in half an hour. You see, this is the delta.codecuisine.ca is a server that I put there, and if you want, you can get an email address here. And who am I? How can you trust me? The point is you don't need to trust me, because I can't read any of your messages because they all come with GPG. One, and what if I shut down my server tomorrow and then you cannot talk to your friend anymore? It's not like that, because you can use any email address that you control to chat with your friend. All you need is your private key, which is on your cell phone. I go down, you change your email address. The moment you send the text to your friends, you make a key exchange, and they know you are the same person. So the authentication comes from the secret key on your cell phone. You're not relying on me to not read your messages, because I cannot, they're encrypted, and you don't trust on me to authenticate you to say, oh, this is the same owner of the email, to check your password that you're the same owner. You don't. You're using open cryptography. You're using your secret key to authenticate yourself to your friend. You say, I'm the same person who had the secret key yesterday, even that my email right now is a totally different server. So that is, you see how much more resilient this than Signal. The other thing, for example, if you go to Doha Airport, Signal doesn't work because they don't like Signal. Here, if they're going to censor emails, then basically they are going to stop all emails in the world. I'm using something that is already used with a lot of people. If they are going to drop all emails in the world, then just to stop people from talking on Delta Chat, then that's a very high price to pay. So even that, it has a censorship resistance. So it's much more resilient than something like Signal, and much more something than, I don't know, like AOL Messenger, something that wasn't end-to-end encryption. The other way to give availability, resilient to your storage, to your data availability, is to use DHT. So there are solutions already there. They use DHT to find your material, IPFS, BitTorrent. That is how BitTorrent works. I can give the address of my data on the DHT. So there is no, if somebody in the network knows it, then they give it to you. It's very hard to take that kind of a network down. Or using other, redundancy solution like Tahoe Labs, which has end-to-end encryption inside it. The other thing that we need to replace sometimes is consensus. So that is basically the part that blockchain will give you. You choose either a random leader to decide what is the truth, to run an operation that is like proof of work like Bitcoin, or you can use a VRF, verifiable random function, which I'll go back to as basically you roll a dice and say the person who got the dice can do the operation because it's distributed. So basically what will happen that, or you can use Byzantine fault tolerance, so people vote on the fact. I'll get back to the Byzantine fault tolerance protocol, but for now I want to talk about VRF, which has much more other application beside choosing a leader. So VRFs are verifiable random function. They are basically, you have a secret key, you have a seed, you generate a random value using your key and the seed. People can verify that you have not cheated. So the good thing about this, you can roll the dice once, but you cannot roll it again if you didn't like the number. So you're doing a deterministic random generation, and people can verify that you haven't lied. But this is basically like using digital signature that I showed you. So I'm going back to that. So when I sign, the signature that comes out is random, but it's deterministic. I cannot sign and get in these signatures that are used for VRF. Every time I sign, I get the same signature is a random number that is generated by me. So the other piece of computation that you want to replace is private computation on private data. So when you go to your bank and you transfer money, the bank completely see everything between the beginning account, the next account, and everything. But you trust them because they're only one entity, and they promise not to tell anybody till they tell the government or somebody else. Here, you need to do something because you don't trust anybody. We are decrease the trust. We don't want to trust. So we need to replace this private computation and data with something else, and that comes with zero knowledge proof, which I showed you a very, very simple example of it there. Or you can use a homomorphic encryption. So that's doing operation on the encrypted data. Without knowing A or B, I can add them together. These are much more primitive than zero knowledge proof. Zero knowledge proof can basically do any operation. This operation that I told you, I take your money from your bank account to my bank account without knowing who are you and who is me and how much money was in your bank account, how much will be in my bank account. You just verify that the operation was done based on the rules of the game. The last thing I want to talk about is proof of personhood. This doesn't have a real cryptographic solution. So currently we rely on government passport to verify people, but you can do like crowdsourced version of this. So at Web3 we are working on this. So if 10 people every week they say you are the same person, then that way it gives you a personhood and you're not an AI bot or something. But after your person who is established in the system, then you can use ringVRF, another thing that is based on ZK, to do operation. For example, you want to give universal income to every single person. They generate a seed using the VRF, and then they run a ZK proof that the seed was correctly set, and you are a person. You generate these two ZK proof, you give it, they send the money to your seed account. If without knowing who you are, and the only thing they trust you are a human being because you ran the ZK proof. Finally, sometimes that you cannot replace this trusted authority. You can crowdsource it with kind of crowdsourced distributed key distribution. In cryptography, that when 2/3 of people, they say yes, then that authority will be yes. But at least it's better because it's crowdsources rather than having single authority decide about everything. This is the detail of how to do crowdsource, but okay. I just say a fast thing. So the thing is based on VRF, but it resolved the situation when somebody wants to cheat by not revealing their VRF. So in conclusion, we can use all these cryptographic primitives and distribution technique basically to eliminate single point of failures. And we can basically get a much more resilient system that, some random person one day wake up and turn the switch off cannot turn off our systems. And then we will have our customers. It's just that much less convenient than a central system. The code is more complicated, the cryptography is more complicated, but in long term, I think, this will reward you with more resilience. So maybe we should get out of our comfort zone and, start developing systems that are more open and more distributed. Thank you very much.
Thank you very much. Are there any questions?
Hello, but I would like to ask you what will happen if the bad state players can mask as users and they infiltrate in this system. It means that they can get data for the user or for anyone that use this service or that want to use this service anonymously. So what stopped them to mask like regular users, regular players? Thank you.
You're welcome. The general approach is I'm not going to trust anybody. So you are not trusting me and I'm not trusting you. So for example, in Delta Chat, as I showed you, I have a server here. You're welcome to join, but you're not trusting me. So that the other users, they should know that this bad actor in the system they should not trust them. So to begin with, they will not put anything unencrypted on that system, no matter how reputable I am. You should not trust in me. You put your trust in mathematics and cryptography. So for example, if I'm a bad actor and I really actually want to see who is sending, like what message people are sending, and because of that I ran a Delta Chat server and brought it here, you look at the system and you see, okay, my message is encrypted. No matter what Syed is a bad actor or a good actor, he cannot do anything about it. The exception is here that I said, when we have this, then for example, you want to do crowdsourced encryption. You want to encrypt something that, you want the authority to decrypt it in future. But there, I say only when 2/3 of the actors are agreeing they can decrypt this message. So as long as 2/3 of the actors are not bad states, then this system will stay resilient much more than one state can decrypt it, which can become bad. I don't know. Like the one that went to Apple and said, bring down the app. So on the central system, one bad actor can bring the whole system down. Here, you at least have the guarantee that if 2/3 of the people are not bad, it will stay resilient.
Thank you. We don't have any more time, so thanks again. Round of applause, please. Yep.